everybody. To this session on Mythbusters is Rust Slam Dunk. My name is Ramya, and I'm an engineer at Momento. And today I'm going to be telling you the story of how we rewrote our platform from Kotlin to Rust and what we learned throughout that journey. So we'll start with a short introduction of what Momento is and what our product is. So we are an early stage startup. We offer a real-time data platform with various building blocks for serverless services like caching, a message bus, durable storage, and more to come in the future. We first launched in 2022 with the very first building block, which was Momento Cache. It's a serverless key value caching service. So think of your application cache and imagine it living in the cloud. At a very high level, our architecture looks like this. We have a control plane, which is responsible for creating and managing the top-level entities. In this case, our top-level entity was a cache. And we have a data plane that offers the APIs that are used to modify the data inside the top-level entities, like the data inside your cache. Going one level deeper, our data plane consists of like two major components. There's a routing layer whose function is to take in an incoming request and send it over to the place where the data lives. And we have a storage layer. You can think of the storage layer as a collection of slices of data. And each of these slices is managed by like a different node or a different partition. In the storage layer, we run different types of storage engines based on what type of APIs or operations you want to do on your cache. So when we first launched, our highest priority was to just get the product out there as fast as we could so that customers can start using it. And we had a diverse team. We had engineers who were veterans, and we had engineers who had just started off in their careers. The majority of us had a background in JVM-based languages, like Java and Kotlin, and some of us had operated at-scale services in the cloud using those languages. So we decided to just use Kotlin to get the product out there. And as you can see, all the components that we wrote were in Kotlin. In our storage layer, we used third-party or open source storage engines, and our routing layer would just talk directly to those engines. So once we had something working, we could finally measure it. So we put in the time to add metrics, set up automated performance tests. And then we came up with a workload that would identify how most customers would use us. And for us, this workload was we started off with a 20K TPS workload of just simple gets and sets with an equal split between the two. And the gets and sets were for small items under 4 kilobyte. And the metric that we were most interested in at this time was the end-to-end latency as measured from the client side, so as measured from outside the service. And we measured this latency with just a single routing node because we wanted to see what we can get from one node. So we established our single node baseline as a P999 latency of 4.99 millisecond and a P99 latency of 4.94 millisecond. And we decided, yeah, this works, and we can just launch with this. So we launched, but no product stays the same. And we immediately had a new requirement. So now customers didn't just want to set and get simple values. They wanted more complex data types, like dictionaries or lists or sets. And we had to make design changes. So now we needed to support a new storage engine that could handle these data structures. And we also now had to support multiple of these storage engines based on what type of operations the cache was going to support. So we needed a new abstraction now, a layer that would present a unified interface for all the storage engines to the routing layer. And we decided to build this layer in Rust because there was already a lot of interest in Rust in the company at the time. We were exploring some storage engines that were built in Rust. And we thought this was a good candidate for an experiment because it's an internal component. It doesn't talk to clients directly. And it's also a brand new component. And the business logic was relatively simple. So it acted as a manager for all the different storage engines, and it was responsible for just routing requests onto them. So we ended up with a V1 version of our stack. We now had like a Rust storage layer, still using different storage engines, and our routing layer continued to be in Kotlin. And we had set up, since I mentioned we had set up automated performance tests, we found a regression. So when we tried to use a cache that was going to support data structures, we didn't change the workload. We used the same one. So the workload was still just doing simple gets and sets. But we found that there was a huge increase in the P999 tail latency. So compared to the old one, it went from like 5 milliseconds to 9.3 milliseconds. And that raised a red flag for us. Now, before I dive into what we did to solve this problem, I'm just going to take a brief detour into like scaling. So all these benchmarks so far have been focused on the performance of a single node. So scaling is definitely a tool that we want to use. And I'm just going to run through like the advantages and disadvantages of the two different types of scaling, like starting with vertical scaling. So this was an easy change to make as long as the application can take advantage of the additional cores and memory. We saw good results from trying to vertically scale the routing node from a C6.2x to a 4x. We were able to cut down the latency to like 3.4 milliseconds, of course, at an increased cost. But we didn't want to use this tool right away because we want to like maximize what we can get out of a single node. Like we will end up using vertical scaling, but we didn't think it was worth it at this point for a relatively low TPS of 20 KT. And the same applies to horizontal scaling. It increases costs. In horizontal scaling, you're just scaling up more instances of the same service. There is more effort required for horizontal scaling. Like, it works great for stateless services like our routing layer. But if we wanted to do that for our storage fleet, we had to like build in functionality to go and like migrate data from one node to another because now the slices of data that are being managed are changing. The second problem with horizontal scaling was that it assumes that you have good load balancing. Now, this wasn't exactly true for us because our data plane interface was essentially a gRPC API, and gRPC uses persistent connections. So the way clients used us was when the client SDK would start up, it would establish these connections to the routing layer, and then it would just continue sending requests on those connections. So adding new nodes would not immediately rebalance the existing traffic, and clients had control over how many connections they decided to establish. So they could choose to just send everything to a single node. So horizontal scaling would help, but it wouldn't really solve this problem completely. And I want to like reiterate why we have been focusing so much on the single node P999 latency. So for us, when we envisioned this product, we wanted to offer latency as a feature. And by that, we want customers to be able to rely on us in the worst case and not just the average case. So our first core goal was to have predictable low tail latencies for this product. And our second goal was to maximize the cost efficiency. So we wanted to stretch the infrastructure to as much as we could and get as much performance as we could out of a single node before we start to scale. So with the core goals in mind, we went back and looked at what was causing the performance regression. In the top bottlenecks, we found that garbage collection was causing unpredictable spikes. We also found that Kotlin was slower on Graviton. Now, Graviton is Amazon's ARM architecture, and we wanted to move to Graviton because it can offer significant performance benefits as well as cost savings up to 40%, which ties back to our goal of maximizing our cost efficiency. We also ran into netty issues. So our Kotlin routing services used netty for the server framework. And one thing that we discovered was that our ePOL threads were very busy. So we went back and tried some optimizations in the existing service because you don't want to throw away what's working without doing a good enough investigation. One thing that really helped us was to tune the number of threads, which was surprising. But when we brought down the number of threads, we got better performance. Another optimization that we added was to have a second ePOL client loop because the ePOL threads were very busy. We added it to netty. The third one, we found that using a direct executor helped us for coroutine callbacks. Again, this was a change in netty. Then we tried tuning the garbage collector. So we were using the G1 garbage collector. And what we found that tuning it to have fewer and bigger memory areas was actually better. There are garbage collectors that claim to minimize tail latency. They've come a long way, but this was 2 years back. We tried it out for a short period of time. And what we found was that it could not really keep up with the pace of allocations that we were doing. So we decided, and in the meantime, of course, the product keeps evolving. So we had another new requirement. We were going to add the second service, which was a serverless event bus. And the idea of this service was to have lightweight topics that users could publish to and subscribe to without provisioning them in advance. And this meant that now we had to add support for streaming gRPC APIs. So prior to this, we had a gRPC server, but it used Unary APIs. Now we had to add streaming APIs so that customers could just call subscribe and then get notified as new messages get published. So we came up with the idea of rewriting the routing service in Rust. And the main goal was to avoid garbage collection. We built a small prototype, a very unoptimized prototype, and it showed that it would help with the benchmark workloads. So even going up in TPS, we were still able to keep the latencies, the tail latencies under 5.2 milliseconds. And we also saw the prototype had much better performance for topics. If we had to launch the topics feature with the JVM-based routing service, it would have cost us a lot more. So some of you might be wondering, why Rust? Well, we love the memory safety that Rust offers, and I personally love that it flags errors at compile time versus runtime. But the Momento-specific reasons for using Rust were there was no garbage collection. Among the choice of non-garbage collected languages. Let's just say that C++ was not really popular. There was strong internal advocacy for Rust among the team, and engineers were like excited to work on it. So usually it's really hard to like balance your business needs with what engineers want to work on. And like using a language like Rust like gave us the opportunity to do that. It was also a good like way to hire in a competitive market. So we were at a fork in the road where we had to like choose between continuing with Kotlin and optimizing it further or moving to Rust. And as I said, like we tried a bunch of optimizations and we had reached a point where the benefits were like only incremental for the amount of effort that we were putting in. We could have delayed this decision, but that just meant that now we'd have to build topics in the old service, and now if we eventually migrate, now there's a lot more area to migrate. We were aware that there are going to be risks to write this service in Rust. The very first one was we are spending developer months in rewriting an existing service compared to building new features and attracting more customers. That's a pretty big risk for an early stage startup. We knew that we won't be able to have like feature parity on day one. So that meant that we had to be able to run two systems at the same time until we had feature parity. We had existing customer workloads on the old system, and we had to migrate those as well. So all of this just contributed to increasing the burden on operators. The last risk I wanted to call out is that the Rust ecosystem is not as stable as older languages. And I'll dive into this one a little bit more later. So when it came to making a decision, we decided to just invest in the future and go with Rust. One of the factors that helped was that there was interest from customers who wanted to measure our performance by running their own load tests against us. And we felt that Rust would give us a quicker path to meeting those expectations. And we decided to do like an incremental migration to mitigate the risks. So we started with implementing only the new service, the topics service in Rust, and then we slowly added like the caching service and the APIs within that service one by one. So that's how we ended up with our V2 version of the tech stack. So we had a Rust routing service and we had a Kotlin routing service coexisting in the routing layer. And we were migrating traffic to one of those based on like the type of feature, whether it was topics or cache or which API in cache. We took a Rust-first approach to any new features. So we started adding new APIs to the Rust. This was to the Rust service. This was like a good way to minimize the blast radius when we were like rolling out new changes. Now, as I said, the majority of our team did not have a background in Rust. So we also like needed to build up Rust expertise in-house. And some of the things that helped us do this was, like, first of all, we switched all our operational tools also to Rust. So this gave engineers a good way to like get experience writing Rust code without the risk of like bringing down a service. The second thing that helped us was to like have reusable patterns established in the code that could act as a template for developers trying to, let's say, add a new API, like, or support a new type of data structure. We created a culture of like sharing the learnings. This was achieved through like having different means like Slack channels, ad hoc talks on different features of Rust. And we used code reviews as a teaching mechanism. So there was a lot of effort spent on making sure that every code pull request was like looked into in detail, and also like in your comments, providing the best way to do that, to achieve something in Rust. So with all of that, we finally had a Rust routing service in production. And if I were to summarize that experience, I'd probably say it was mostly harmless. I'm also mostly kidding. It was a smooth experience. So with a few callouts. A lot of, when I mentioned that the Rust ecosystem was not stable, what I wanted to say was that a lot of the popular crates for server frameworks like Tonic, which is the crate used for the gRPC server client implementation, these crates are still on unstable versions, so you can't really rely on them. Hyper, which is the crate for HTTP server client-server implementation, made breaking changes when it went to V1. And it required us to like refactor our code to like write a TCP accept loop in 2024. The third point I want to call out is that it's not just the changes that you're aware of because it's breaking your compile time builds. You can also like pick up bugs just by picking up a new minor version in an unstable crate. This happened to us once, pretty recently. There was a change in the accept loop for TLS servers in Tonic, which I mentioned is the gRPC server implementation framework we use. And that brought down our service in production. Like the loop was changed to treat any IO error during establishing a TLS connection as a fatal error, and that shut down the server. So you can imagine, like, this is a pretty big change. And it took a while for us to like debug the issue because, again, this was not obvious in a code review. It was a version change, a minor version change. So let's talk about performance now, since performance was one of the main reasons we switched to Rust. So, it's an unwelcome truth, but you can write slow code in Rust too. Rust gave us a great initial boost to performance, but as we tried to scale the limits of what a single node could do, we ran into more performance issues. And these were actually like Rust specific, or they were more, to be more accurate, they were related to the way the gRPC ecosystem works and the way our specific use case. So I'm going to dive into one such example. So initially, we were not able to scale beyond 20K TPS on a single node using Kotlin. With Rust, we were able to go to like 32K TPS for the same benchmark workload. But what we found was that at 32K, our tail latencies would just like spike to 100 milliseconds. So there was no graceful degradation. It was just under 5 milliseconds and then a sudden spike to 100 milliseconds. So we started digging into that. And the clues that helped us along the way were like, we had metrics on both the routing service and the storage service. Now, the routing service metrics were reporting that they were seeing a lot of delay talking to the storage service. But the storage service metrics said that, no, they were fast. Like the time from when it got a request to when it sent a response was like very, very low. We tried vertically scaling, and it doesn't always help, and it did not help in this case. We added more observability. So we used Tokyo as the async runtime, and Tokyo provides metrics on the tasks that are scheduled in the runtime. And we got one hint from them. We saw that the long scheduling delays for the tasks were increasing as we increased the TPS. But this was not really sufficient to find the root cause. So then we went to get some flame graphs. And what we found was mutex contention. It's a little bit hard to see in this slide, but you'll see that there's a lock contended call on a sync mutex there. And it's being called from the H2 crate from, let me see this, sorry. Yeah, from the send response function. And we identified the root cause to be a long-standing issue with the H2 crate. Now, H2 is the crate that's used for the HTTP protocol implementation for both HTTP 1 and 2. And this particular issue had been open since 2021. And the crux of the issue was that HTTP 2 uses multiplexing. So on a single TCP connection, it has this concept of a stream, which is like an independent sequence of messages. And what H2 was doing was it was using a mutex to coordinate between different streams on the same connection. Now, why did it impact us so much? Like, what caused the latencies to spike to 100 milliseconds suddenly? As I mentioned, we use gRPC for both the routing service and the storage service. Our routing service is essentially a reverse proxy. It's taking in requests, it's sending them off to the storage service, and getting the response, sending it back. The client talks to the routing service via gRPC channels, and the routing service talks to storage service on gRPC channels. Now, by design, we don't want to be establishing new channels internally from the routing service to the storage service. So we use a small number of persistent channels there. And on the client interface side, there are a lot more of these channels. And I'll explain what a gRPC channel looks like at a very high level. So a gRPC channel is managing one or more HTTP connections. In our case, we only have one HTTP connection per channel. This is very language dependent, so it depends on the SDK. The gRPC channels are like scheduling RPCs, which you can, for unary APIs, you can think of the RPC as just like a request-response pair. And the gRPC channel multiplexes RPCs onto the underlying HTTP2 connection by mapping each RPC to like a different stream. So by design, since we have fewer channels between the routing service and the storage service, we have more streams per connection on that side. And that meant there was a lot more contention because, as you remember, there's a sync mutex being used to coordinate access to these streams. And then we used a Tokyo multi-threaded runtime. So the Tokyo multi-threaded, so you can imagine each request that's coming into the service as a task that gets scheduled onto this runtime. And the way the Tokyo multi-threaded runtime works is it has one or more workers, each of which is mapped to like a thread. Each of these workers has its own task queue, and then there's a global task queue. There's no way we can control which tasks go to which worker. So what was happening was multiple RPCs from the same connection could get picked up by different workers. And now suddenly we have two workers running on two different threads competing for the same mutex, which is again a sync mutex. Just to give a brief overview, a sync mutex essentially means that while a thread is waiting for it, it's not going to be doing anything else. So every time we hit this contention, let's say one of the workers, we had only two workers and one of them was waiting for the mutex, we lost like 50% of our processing power in the server for that duration. So we started looking at solutions for this. The first solution was to like use a different lock implementation, like not this standard sync mutex. And that showed improvement. But the H2 crate is like pretty far down the infrastructure stack. And patching it means that we are just like entering dependency hell. There was like no way we could have managed that in a sustainable way while continuing to upgrade the versions of the crates that we are using. So we tried that out. We saw improvements, but we chose not to implement that in the service. The second solution that we tried was that since we saw a lot more contention on the communication between the two internal service, between the routing service and the storage service, we decided, like, why not just split that work onto a different runtime? So now, yes, that communication could still lock up threads, but it wasn't locking up the same threads that were being used to serve the requests that were coming from the client. So that helped, although it did have a drawback. So when you're spawning new tasks outside a runtime, they are like a lot more expensive to schedule. But when we measured the performance for this, we actually found that the benefits outweighed the drawback. And we were able, with this approach, we were actually able to scale the single node throughput to like 40K from 32K. And the P99s stayed under like 10 milliseconds. We could have actually gone a little bit further without hitting the 100 millisecond here as well. But this was not really enough for us, so we decided to like go back and find another solution. And this slide here shows a very simplified representation of how a gRPC service in Rust looks like. There are like multiple layers of abstraction. So the stack starts with like Mio at the bottom, which is used for low-level I/O, that then interfaces with what the operating system is offering. We have Tokyo, which is the async runtime on top of it. And Tokyo is managing or scheduling the tasks and like executing them, making sure they're executed. And we have Hyper, which is the HTTP client server implementation, followed by Tonic, which is gRPC client server implementation. Now, Hyper is the one that uses H2, where we discovered the bottleneck. So we decided that it might be better to like maybe just get rid of a few of these layers. And what we ended up doing was like, for the communication between the router and the storage service, since this was internal to this system, we could control it. So we decided to get rid of Tonic and Hyper there. And we built a new library. We built something called Protosockets. Protosockets is a way to like exchange messages over raw TCP connections. These messages can be encoded in any protocol that you choose. And we used protobuf for this, since both of these services were like already gRPC and already talking protobuf. So we got rid of the top two layers, and then we just had the business logic in the application use Protosockets to talk to the storage service. So this is what it looked like after that change. So now the client interface remains the same, but in the inter-service communication, we are using Protosockets. So we are bypassing H2 completely. And that gave us pretty good gains. So we were able to go from 40 to 65K TPS on a single C7G.2x large instance. And the P99 was like, P999 was still under 10 milliseconds. We stopped at this point with the Rust-specific optimizations. We might actually go back to it in the future, but for now, we stopped at that point. While talking about all these different optimizations we have been doing that are Rust-specific, it's important not to lose track of other simpler things that you can try out. One such change was just upgrading Amazon Linux 2 to Amazon Linux 2023. It gave us, without any other changes, just that change, it let us get to 75K TPS from 65K. And our latencies decreased at every percentile. So earlier, the highest we were seeing was like around 10 milliseconds at P999. It even went down to like 7.5 milliseconds. There are other changes as well, like choosing the right instance type that can offer significant performance benefits. This is where we are right now. So we have gotten rid of the old JVM-based routing service. So our storage layer and the routing layer are both using Rust. We've been slowly migrating parts of the control plane as well. And the reason we were doing this is the control plane does not really need the scale that the data plane has, but having a unified language for the backend improves code reuse, and it's easier to maintain and less burden for the engineers. We have been building new control plane components as well in Rust, and we are slowly migrating the existing one. So looking back, would we do it again? And my answer is a yes, but it's a qualified yes. The main reason for that asterisk out there is that the hit that we took to feature velocity was like a real business risk. And it might not pay off again because external factors don't always remain the same. So if we were sure that that risk would pay off, then I would say, yeah, unconditionally, yes, it was a good decision to move to Rust, because it let us offer the guarantees for the latencies that we wanted. It let us gain more customers because we were able to meet the load test expectations that they had. And we were able to launch more new features cost effectively rather than over provisioning and like spending a ton on infrastructure. On the con side, of course, like I said, the hit to feature velocity was a risk. The unstable ecosystem and the constant changes in the crates that we were using could cause cost outages and could potentially cause more. When we discovered problems in the low-level crates, the effort that was needed to get around them was quite a lot. With that, I'll go to the question of whether Rust is the right choice for you. I mean, even though it was the right choice for us. And I'd just say that the best solution is not the one that's like recommended by most people. It's the one that's tailored to your specific problem. And when choosing the solution for your problem, the things that you should consider are like, what are the SLAs you want to offer? Like, if your product does not need to serve millions of TPS or hundreds of thousands of TPS, you probably don't, and you do not have tight latency constraints, you might be better off with a different language. The second aspect is like the business risk, like what stage are you in? What's the main goal, the business goal? Like, are you trying to just attract more customers and like grow revenue? Might be better to just throw money at the problem and just go with an existing simpler solution. Are costs a concern? Again, over-provisioning is good. I mean, it can help solve the problem if you can just throw enough money at it. You also need to consider like how long it takes developers to ramp up on Rust. How frequently are you seeing churn in your engineering teams? How much does your application rely on third-party tools and libraries? Since the Rust ecosystem is fairly new, you might not find all the libraries that you're looking for compared to like JavaScript or like Java. So with that, I'm going to end my part of the presentation and open up the floor to questions.
Thanks. Is this on? Yeah. All right. That was really interesting. Thank you for that. Do you find that developers are as productive in Rust as they are in Kotlin?
It's been a while. I would say that our productivity has increased over the last year. When we first started, they were not as productive because Rust does have a steep learning curve.
So you think it's just the learning curve, but at some
but
point...
Now I think we are more productive because we have established like these patterns in the code. So there is a template to follow like when you're adding a new API. So that makes it faster and improves the productivity.
But did you actually measure that?
The developer productivity?
Yeah.
No, we did not. We did not have
patterns with Kotlin. Would you see the same productivity gains with Kotlin?
Probably, yes. I would say that. Yeah.
Can you say a little bit about like how long that learning curve is and like what are some of the most challenging things to adapt to when you're moving from a language like Kotlin to a language like Rust?
Sure. I would say to just bypass the problem by using like an unsafe feature. That was one of the things that I personally found hard. Well, actually, I'm not comparing it with Kotlin. I'm more comparing it with C++ in my mind. Can you just repeat your question? I think I might have missed part of it.
Sort of like a timeline, like how long do you think it takes a developer who's familiar with something like Kotlin to get them?
So the question was, how long does it take a developer who's familiar with Kotlin to get familiar in Rust? That's going to depend a lot on the individual developer, but if I were to just like throw out a number there, I would say probably a month. And I would recommend that they start off with writing non-production code in Rust to just gain experience.
Hello.
Hi.
I just a bit of a sidebar question, but you were showing tooling around your performance metrics and obviously like doing that through load testing. Could you comment on maybe tools that you're fond of or things that were useful and doing that on a regular basis?
Sure. So for the load generator, we use a tool called RPC Perf, and one of the authors is actually in the room with us, Brian from IOP Systems. We work closely with them to develop new features onto RPC Perf as well. It's a load generator that's also written in Rust, by the way, and it can send like a very high amount of a high TPS of requests to your service. They also develop a tool called Serverless, which is a telemetry agent designed for very low-level system metrics at high resolutions. So things like how many syscalls are being called, or like how much lock contention are you seeing at the OS level. So we use Serverless to gather those metrics. For flame graphs, we just use the cargo flame graph crate. Yeah.
Yes, hi. Maybe I missed this part, but I was wondering if garbage collection was the main bottleneck or one of the bottleneck. Have you tried to run without a garbage collection on the JVM side?
Do you mean just turning it off completely?
Yep.
We did, and we ran out of memory very quickly.
No, you can. Like there's the epsilon garbage collection, or really rewriting parts of it and disabling it.
I don't think we tried completely disabling the garbage collector, to be honest, but we did try making it run like less frequently.
Yeah, by increasing.
By
yeah,
yes,
okay.
and that did not help us because like we are doing a lot of allocations. Like every time a new request comes in, we are allocating like new memory for that request based on the item size that's being operated on, and it did not like help us. Like we ran out of memory.
Thank you.
I think we have time for a couple more questions, if you have any.
This may sound critical, but it sounded like you went to Rust just because your developers thought it was cool and it was hip. Is that correct?
That was one of the factors.
Did you do any analysis on other languages before you jumped into Rust? I mean, did you do any analysis on Kotlin before you picked Kotlin?
We did not do analysis on Kotlin because we had developers who had used Kotlin for I personally worked on a Kotlin service in AWS that would handle like hundreds of thousands of TPS. So we did not actually do a lot of analysis on using Kotlin. At that time, our priority was to like just minimize the time it took to launch. And we did, and as I said, we just did not explore other garbage collector languages. Because we decided we just don't want garbage collection. And I mean, as I said, like C++ was not a popular choice. We were also exploring storage engines that were written in Rust, so it would have helped to have a unified language for everything. So that's another reason we settled on Rust.
Thank you. One last quick question. How long were you using the Kotlin system before you transferred over to Rust?
Around like a year.
Thank you.
Yeah.
So you mentioned the the tooling that you use for Rust for RPC perf and Resolution licensing on those, or maybe if you know off the top of your head, or Brian. What's the license model?
They're Apache too. They're open source.
Oh. Yeah, thanks for mentioning that. I forgot.
I have an addition too. We have. Okay. Really good question around Rust. I do think that for us as an early stage startup, a lot of the decisions aren't purely technological. In fact, most of the decisions are engineering in terms of like human driven, meaning that you have to have something that gets the team excited and unifies the team and moves us forward as a unified whole. And that's why I think it ended up being not like a purely programming languages analysis, but more like what does the team feel excited to go and quickly implement and get it out to market. And that ended up, we ended up picking Rust for that reason. Thank you very much, everybody, for being here. We'll take a break and we'll be back for the next excellent talk by Alex.